So now we have the final lecture on this topic of seismic design concepts. As mentioned previously, an earthquake is a random and unpredictable event. The dynamic behavior of structures is also very different and much more complex than in case of the static effects. Considering these two, the analysis of seismic effects on structures is becoming more challenging. Analysis methods in seismic engineering can be grouped from the most simplistic to the most complex, as shown in the table. These methods are classified as either being static or dynamic, and linear or nonlinear. Several methods should be taken into account when thinking about these methods. For example, in case of static analysis, a single and constant force is considered, whereas in dynamic analysis, the value of the force changes during the analysis. Furthermore, linear and nonlinear analysis are mostly related to how material, section properties, and geometry are taken into account. As discussed in session 3.2, when linear methods are used, a response modification factor is introduced to simply take into account the nonlinear behavior of members. Analysis methods can then be listed as follows: equivalent lateral load method, response spectrum method, pushover analysis, and nonlinear time history analysis. The most accurate and reliable method is the nonlinear time history analysis, which is also the most complex one, since creation of the analysis model is complex due to definition of nonlinear properties. It is also a complex procedure to obtain or create input motions which have high impact on reliability of the results. Furthermore, the time that is required to solve the problem is relatively long. And last but not least, the interpretation of the results is complex and requires extensive experience. Numerical analysis methods such as direct integration can be used to solve the problem and obtain a time history response of the structure. The analysis is done by step. A time step value is determined and analysis needs to be repeated for each time interval. The response can be obtained at all joints of the structure, and one of the most important values to check is the top displacement history, as you can see in the graph. The results obtained or the design completed using this method will be more realistic if all steps from selection of input motions to proper modeling of nonlinear behavior are well covered. Compared to the other methods, these results will provide less conservative design solutions. To better understand the response of the structures and to simplify the problem, the model analysis method has been developed. The response of structures are decomposed to different mode shapes, which are considered to be independent from each other. Each degree of freedom of the structure has a separate mode shape. Each mode shape has a different contribution ratio from the total behavior of the structure. This graph illustrates how different mode shapes are separated from the total behavior of the structure. In this case, a 3-degree of freedom system is analyzed and 3 different mode shapes are shown. When each mode shape is analyzed by using earthquake records and the results are superimposed, this is called a model response history method, and it gives very close results to time history methods. Now, let's have a look at a more simplified approach, the response spectrum method. In this case, a force value is obtained from the design spectrum for each mode shape, and analysis are based on that single force value for each mode. In other words, the peak response for each mode is taken into consideration, and they are combined even though they are not occurring at the same time. That's why this method is more conservative than the others mentioned above. Real structures have numerous degrees of freedom and hence numerous mode shapes. The contribution of each mode shape is generally defined by the model participating mass ratio or effective model mass. The model participating mass ratio is the mass represented by each mode shape divided by the total mass of the structure. Generally, it is not practical to make the calculations for all modes. Design codes accept the total participating model mass ratio to be more than 90%, but not necessarily equal to 100% of the total mass of the structure. For structures with a regular, symmetric configuration of their structural system, and with a limited total height, the contribution of the first mode is expected to be governing, which means that the model participating ratio of the first mode shape is higher than 70 or 80%. In such cases, it is allowed to take only the first mode shape of the structure into account. The loading values are calculated by distributing the base shear to each floor with respect to the first mode shape. This is done by defining a static force that is derived using the first mode properties. This simplified method is named as equivalent lateral load method. A similar static loading is used together with nonlinear analysis in case of the pushover analysis methods. The structure is forced with unit forces acting in the shape of first mode, and the locations of plastic hinges are found iteratively. The final result of the pushover analysis is the capacity curve, which gives the actual performance level of the structure. If the structure is irregular or tall, which means that contribution of higher modes becomes critical, then model pushover analysis should be applied. In this case, not only the first mode shape, but also higher modes are used like with the model analysis. This was the last lecture about seismic design concepts. Thank you.